So the last time we looked at the cell potential with respect to the standard hydrogen electrode of zinc, and we calculated that to be 0.76 volts. Okay, and so of course on the table here, so these are both listed, the copper and the zinc oxidation here. These are both oxidations. So if you look at the chart, you will find those numbers to be in the opposite, 0.76 volts, and this is going to be plus 0.34 volts. And so it's come to my attention that this chart that I have is, you can't read it. So I recommend that you pause and go print it, or at least have access to it. I'm going to make an attempt to zoom in on it as much as I can, but the quality is pretty poor. So but you should be able to look at this chart and use it properly. So let's do that. But my point here is that if you were to predict which way the electrons flow, is copper oxidized or zinc, only one can. And so if you find the electron potential on the chart, the one that's has the lower number, in this case it's going to be the zinc, it's going to be the one that's oxidized, and the other one is reversed, the other one is going to be reduced. So this will be the anode and this will be the cathode. And let's take a look at a real example and work it all the way from scratch. Alright, so here we have aluminum and nitrate forming aluminum ions and nitrogen monoxide. So we can right off the bat tell that aluminum here is oxidizing to aluminum ions. 3 electrons would be ejected here, and so it's got to be the nitrogen that's being reduced. So here we have nitrogen is +5, so we have the nitrate, and then it goes to plus 2 here, so there are 3 electrons. So that works out nice and neat, doesn't it? Nitrate goes to NO. And so if we go to that chart now, and I have zoomed in, hopefully we can look at that. If you find the nitrate here, reduction, nitrate is already written in that way. It has an electron potential of 0.96 volt. If you come down to the aluminum, it's here. It has an electron potential of -1.66. So it's the nitrate that's going to oxidize the aluminum, which means that the aluminum is going to be the anode and the flow is going to be to the nitrate. So we're going to reverse the way it's written. It's already correct, right? So this will be a spontaneous reaction. So this is already written in the reverse as the anode, and this is the cathode. And so if we were to now calculate, and I guess I got to get those numbers, and I'm going to keep the numbers as reduction potentials. Okay, it's just easier for me. -1.66 volt. Of course, the way this is written, the electron of the way of the oxidation here would be +1.66 because it's reversed. But if I write it this way, I can tell which way it flows and calculate the electron potential. Now this one here is 0.96 volt, which I know this is the anode and this is the cathode, and I have an electron flow. This is spontaneous, and I can calculate the electron potential of the cell. It's the cathode minus the anode, and so that's going to be equal to 0.96 volts minus -1.66 volts, which equals to 2.62 volts, and that is spontaneous because that's a positive number, but I can tell because I kept it as reduction potentials. Now, if we were looking at the reverse reaction, then our electron potential, so meaning this is written in the reverse reaction and this is written in the reverse reaction. So if this was the anode and this was the cathode, our electron potential would be minus 1.66 volt minus 0.96 volt, which of course is negative 2.62 volts, and that negative means that this is running in the reverse reaction. This would not be a spontaneous reaction. So you should be able to do that. Always be careful when you fish out these redox reactions that you've got the right one, because let's see if I can find a good example here. But yeah, look at iron. This is iron and 1 electron going to iron plus 2. There's 2 more on this chart. Of course, they're not shown here because they're higher up or lower, where you have iron 0 going to iron 2 plus and also iron 0 going to iron 3 plus. So there are 3 different reactions, and so you need to make sure that you pick out the right one when you are calculating these electron potentials. So this is just a summary of what we just did. And you can practice that yourself with a chart. You can calculate the electron potential of this reaction. You should be able to tell me whether it's spontaneous or non-spontaneous. And so let's practice a few more. Predict spontaneous redox reactions, sketching electrochemical cells. Okay, so we also want to sketch electrochemical cells. So I'm going to write out the oxidation here. It's going to be iron going to iron 2 plus and 2 electrons. And so this is, and I'm just going to go to the chart, and I'll do it in a minute. Let me write all those reactions down. And then magnesium and 2 electrons would be going to magnesium. So this is the oxidation, this is the reduction, this should be the anode, and this is the cathode. And for this reaction we also have iron, so that's the same thing here, 2 plus and 2 electrons. That's the oxidation, or our anode. We'll look up the value here in a minute. And then we have lead 2 plus and 2 electrons. That's our reduction. So next we can do a couple of things. You can do this visually, by the way. PB visually. Hang on. Just by location on the chart, right? So what we're looking for is if magnesium is listed lower, if this reduction is listed lower than iron, then it's going to be spontaneous. If it's higher, it's going to be non-spontaneous. And the same is true here for lead. So if I go to this chart, we can now find that lead is they're all in the negative range, but it doesn't matter. Here's lead, here's iron, and here's magnesium. So this is going to be spontaneous, and this is going to be non-spontaneous because it's above. So let me write down those values. We can look at that numerically, right? So iron is minus 0.45. Minus 0.45. The bad memorizer, but the lead is minus 0.13. So here we go. This is the more negative one. This is going to be spontaneous. Whereas this here, the manganese has a magnesium has a minus 2.37. So this is going to flow this way spontaneously. Therefore, question number 1 is already determined. I'm not asking for you to calculate the electron potential, but it's cathode minus anode. So you would take minus 2.37 minus 0.45, which is still a negative number, so non-spontaneous. But here the cathode minus 0.3 minus minus 0.45 would give me a positive number, so this is spontaneous. So the sketching part, all right. Anyway, this is just a beautiful summary here, and I am not calculating the electron potential here, but you can. And this is wrong. This is hang on, let me go back just to verify. Yeah, it's wrong. It's 2.37, not 0.237. So this is minus 2.37. And then, yeah, that would make that wrong, because then that would flow this way. So I guess I'm glad I caught that. Sketching it. Okay, so I'm gonna make this crazy attempt to sketch that, right? So, but what you need is, you need two cells, each with an electrode. You need a salt bridge with an electrolyte, and then a wire connecting. So that's always, oh, that's so beautiful, right? And so if I want to have the oxidation on the left, so the anode, so I'll make this negative. This would then be iron. This is the cathode, is positive, so that would be lead. And so and the flow would be from negative to positive, so that way. And so here I would have iron, and here I would have lead ions. Okay, I wonder if I forgot something. I might have, but and then, yeah, the concentrations, if you wish, for the standards would be 1 molar. Oh yeah, I forgot to label them anode and cathode, so that's also pretty important. So you want to label this the anode and this the cathode. I think I said it, I just forgot to label it. So anyway, I probably won't ask you to label that, but you should be able to tell me which way the electrons flow, which one the anode and the cathode is, so that's no problem. All right. Okay, so I just reviewed and noticed that I made a tiny mistake, not a big deal, but those two reactions we looked at, they're going to flow from magnesium, and I said that was correct and spontaneous, but obviously it's listed the other way around, and so this is going to be spontaneous, going from here to here, meaning the iron is going to oxidize the magnesium and not the other way around. So that would be a non-spontaneous. This reaction would be non-spontaneous, but from here to here would be spontaneous. That's all. So when we come back, we're going to look at Gibbs free energy and equilibrium constants. See ya.